Using mathematical induction and the definition of the number of combinations r out of n, prove that the sum for r from 1 to n of the number of combinations 1 out of r is equal to the number of combinations 2 out of n plus 1 for all n is positive integer. First of all, what does this sigma notation mean? It means that we should consider the first possible value of r, it's 1, and just substituting 1 for r, we get the number of combinations 1 out of 1 plus, and we consider the next possible value of r, it's 2, so it becomes plus the number of combinations 1 out of 2, and plus so on up to the last possible value of y, it's n, so plus the last term, it's plus the number combinations 1 out of n. So as usual, we start with the smallest possible value of n, and we write for n is 1, the left hand side becomes what? It's the sum for r from 1 to 1, the number of combinations 1 out of r, and we can see that there is only one term when r is 1, and it becomes just the number of combinations 1 out of 1. Actually, you may remember that it's 1, or you may use the definition to calculate it. It's not necessary to write in detail using the definition, but actually you may write that it's the larger factorial, it's this 1 factorial, the smaller 1 factorial, and 1 minus 1 factorial. 0 factorial is 1, so it's 1. It's not necessary to write this in detail, you may write just the answer that it's 1. And the right hand side becomes what? The number of combinations 2 out of 1 plus 1, 2, and again it's just 1. Using, you may just remember when these values are equal, it's just 1, and for example 1 out of k is just k. You may remember from the binomial expansion or something like that, or just using this formula. This formula is also given in a data booklet. So as the left hand side is equal to the right hand side, true for n is 1. The next step is, as usual, we write assume true for n is k, and just rewrite this, substituting k for n, so it becomes the sum for r from 1 to k, the number of combinations 1 out of r is equal to the number of combinations 2 out of k plus 1. The next step, as usual, we consider n to be equal to k plus 1, so we write for n is k plus 1, and this becomes the sum for r from 1 to k plus 1, the number of combinations 1 out of r is equal to, and actually what is our aim, what should we get? For n to be equal to k plus 1, it's to be true, we should get the next, that it is equal to what? The number of combinations 2 out of k plus 1 plus 1, k plus 2, and using the definition it becomes what? The larger factorial, k plus 2 factorial, the smaller factorial, so 2 factorial, and the larger, k plus 2 minus the smaller, so it becomes k plus 2 minus 2 factorial, or just k factorial. So we should get that this finally is equal to this, to be true for n is k plus 1. Then, as usual, to use or to be able to use this from assume, we split this sum up to k plus 1 into what? The sum up to k and plus just what? The last term corresponding to k plus 1, and it's what? The number of combinations 1 out of k plus 1. And then we substitute this for this, and it becomes what? The number of combinations 2 out of k plus 1 plus the number of combinations 1 out of k plus 1. And definitely to get this, we can what? Rewrite the obtained expressions using the definition with factorials. So you may just use a formula. I remember this formula, so it becomes the larger factorial, k plus 1 factorial, the smaller factorial, it's 2 factorial, which is just 2, because it's 1 multiplied by 2, and larger minus smaller, so k plus 1 minus 2 factorial, which is k minus 1 factorial, plus k plus 1 factorial divided by 1 factorial, which is 1, and the larger minus the smaller, k plus 1 minus 1 factorial. And definitely we need what? A single fraction, so we should do what? A common denominator. But notice that the least common multiple for k minus 1 factorial and k factorial, it's what? It's not their product, it's just k factorial. Why? Because, for example, if k is 10 and k minus 1, it's what? It's 9 factorial. And what is 9 factorial? It's 1 times 2 times 3 and so on up to 9. And 10 factorial is what? 1 times 2 times 3 times 9 times 10. And you can see that the least common multiple is just this expression. So the least common multiple, and hence the common denominator, becomes just k factorial. It's for this and for this, and definitely we should include this too. So for this the additional factor is what? It's just k multiplied by k plus, I hope it's clear, because if it's 1 times 2 times 9, if it's 9 factorial and 10 factorial, it's 1 times 2 times 9 times 10, and we just multiply this by 10, but it's just the last value, just k. Or it's because k factorial, it's what? K minus 1 factorial multiplied by k. And plus 2 multiplied by k plus 1 factorial. Because for this additional factor, it's just 2. And we can see that we can factor out k plus 1, and it becomes k plus 1 factorial multiplied by what? K plus 2, and divided by 2k factorial. But what is k plus 1 factorial multiplied by k plus 2? It's like 11 factorial multiplied by 12, and it's what? 1 times 2 times so on up to 11, and together with 12 it becomes just 12 factorial, and hence it becomes k plus 2 factorial. It's k plus 2 factorial divided by 2, and 2 multiplied by k factorial, but 2 it's the same as 2 factorial, and you can see that it's absolutely the same as required. And we can write that it's the number of combinations 2 out of k plus 2. Or you may write like this, it's k plus 1, k plus 1 plus 1. And you can see that it's true for n is k plus 1. So we write true for n is k plus 1. And a conclusion: if true for n is k, true for n is k plus 1. Since true for n is 1, because the first step, it was what? For n is 1, so right? Since true for n is 1, true for any n is positive integer. N is positive integer because it is given n is positive integer. And that's all for this question.